As we just saw, the first basic tenet of 21st century flood risk wisdom, that flood exposure is location specific, is actually thousands of years old. Now we'll address the first fundamental modern tenet, that flood hazard is a mathematical curve. We'll clarify that asterisk. A little warning, this part is a bit longer than the others, but I guarantee you'll learn some very important things. In contrast to the wise approach to flood hazard that I'll be explaining, there are three common foolish approaches. We often hear family and neighbors talk about flood hazard as if a generation or two were a sufficiently long enough time to provide a proper gauge of rare extreme floods. But that would be like saying they didn't think their house could burn down because they hadn't seen their or their neighbor's house burn down before. Number two is foolish because it ignores that flood conditions are always changing significantly. Natural wet and dry climate cycles can last decades. Rivers and shorelines change. Floodplains get developed, and greenhouse gases affect rainfall, hurricane, and sea level trends. A wise approach to flood hazard has to take a very, very long-term perspective. We're talking thousands of years. And finally, it is also extremely foolish to think of flood hazard as binary, that any specific location either simply does or doesn't have flood hazard, that we could simply look at a map and say we're in or out. To get beyond the black and white binary, there's a tendency to want to use shades of gray. These three figures are from websites that offer flood hazard rating scores or factors. But the problem with qualitative gradations is that they arbitrarily simplify rather than just measure flood hazard. And they are klutzy for doing real quantitative analysis, like cost-benefit, return on investment, and optimization. Obviously, dumbing down something as important as flood hazard cannot be wise. All hazards, in fact, have a mathematical description. Flood hazard is measured by how often a particular flood level is reached over many thousands of years. We call this numerical rate a frequency. For a specific location, an extreme flood level reached, say, 10 times in 5,000 years has an average frequency of once per 500 years. Hydrologists refer to this 500-year number as a recurrence interval or return period. Importantly, this 500-year number is an average and not an exact interval. It's just like your average heart rate. Say you take your pulse for a minute and count 120 beats. The average frequency is 120 beats per minute, or 2 beats every second, and the average interval is half a second. In mathematically describing a hazard, the term frequency is the same thing as probability, chance, or odds. These terms all refer to the number represented by 1 over the return period. In this example, 1 over 500 years equals 0.002. We can also say this is 0.2%. Technically, hydrologists call this the annual exceedance probability because it represents the chance in any year of a flood level being reached. This means the chance for each and every individual year. Of course, all hazards, including flood hazard, involve many potential magnitudes, each with its own frequency or return period. Obviously, higher flood levels are rarer and have lower frequencies, the same thing as longer return periods. But of course, your average heart rate changes too, such as with exertion. To mathematically understand how your heart rate, the frequency of your heartbeat, changes versus exercise, cardiologists graph the relationship with a curve. Here's a typical way that hydrologists graph flood hazard. with more extreme flood levels on the vertical axis and longer return periods or lower frequencies on the horizontal axis. Let's say that at some particular piece of property, that once in 500 year chance flood, the 0.2% AEP flood, has a flood level of 57 feet. This is shown by the blue dot. Here are some more frequencies for this location and a smooth curve to connect the dots. For this particular location, a flood level of 21 feet has a return period of 1 year, or an annual chance of greater than 99%. At 25 feet, the return period is 10 years, or an AP of 10%. At 48 feet, 100 years, or 1%. At 58 feet, 1,000 years, or 0.1%. And at 59 feet, 10,000 years, or 0.01%. This graph curve covers a full spectrum of hazard frequencies. Note that the horizontal scale is modified to show equal orders of magnitude using a logarithmic scale. This particular curve has the shape of a slanted S and is often seen in hazard curves. It first rises slowly, then steeply, and then flattens out as it approaches some maximum. Perhaps you noticed that the heart rate graph was also an S-shaped curve. A very important feature of flood hazard curves is that they are in fact fuzzy. This is a way of saying that hydrologists, like scientists dealing with other natural phenomena, like to show that while these curves are able to mathematically describe the full scale and general shape and range of a flood hazard, mathematically they are not very precise. The bars show that the return period, or AEP, for particular flood levels might really fall within a pretty wide range. We can attribute the range of uncertainty to all the random errors in various data and other inputs used to estimate the curve. Hydrologists work very hard to eliminate any consistent error, also called bias, from distorting the curve. However, there's only so much we can do to reduce random errors. To have a really precise flood hazard curve, a hydrologist would need a very long gauge record, typically at least 10 times longer than the longest return period to be graphed. Thus, to graph up to 500-year return periods, a hydrologist would want a record of 5,000 years. A hydrologist also needs to be sure that sea level, storm, runoff, floodplain, and other conditions have been stationary over that 5,000 years. But very long-term stationary records don't exist anywhere. If there are at least several decades of gauge data, the hydrologist could employ statistical extrapolation methods, but these have lots of simplifications and assumptions. If there isn't good gauge data, then the hydrologist has to create a synthetic record using rainfall frequency curves and models of runoff hydrology and flood flow hydraulics. Needless to say, using a synthetic record involves even more uncertainty than extrapolating from a multi-decade gauge record. Here's a 6-decade NOAA coastal gauge record with their statistically extrapolated curve, plus 2 additional upper and lower uncertainty bands to illustrate what we call a confidence interval. The vertical scale has been modified from the website, which is in meters. The main curve shows a flood level of about 7 feet for the 100-year return period. Using the horizontal scale, the upper uncertainty band shows that this flood level of 7 feet could easily really have a return period of less than 50 years. That's half as long and represents a huge uncertainty. And that's when hydrologists have 6 decades of gauge data. Let's take a look at rainfall frequency uncertainty. Rainfall records are often much longer than river and tide gauges, And statistical extrapolations have the advantage of incorporating multiple stations in a climate region. In this figure, the estimate for a 24-hour duration accumulation for a 100-year return period in Baton Rouge, Louisiana, is about 12.2 inches. But the upper uncertainty band shows that a 12.2-inch 24-hour accumulation could easily have a return period of much less than 100 years. This is less uncertainty than the previous tide gauge figure, but again is still pretty big. The challenge with flood hazard curves developed from synthetic records, which are most of them, is that the uncertainty gets substantially increased by issues with the hydrologic and hydraulic modeling. The scale, shape, and general range of graph curves provide a very important and very useful quantitative understanding regarding flood hazard. But the particular curve values for flood hazard are scientific hypotheses. In any science, hypotheses come with uncertainty. In the case of flood hazard curves, the uncertainty is so big that it might be fair to call them scientific guesstimates. With so much uncertainty, you'd be entitled to ask, what's the use of having a curve? We'll see in the next part why a fuzzy curve is a lot more useful than a score or factor. Before finishing with flood hazard, there's one more critical thing to consider. The curve we've been looking at has used a horizontal scale of annual chance. We must keep in mind that most exposures to flooding are not just for 1 year. Most exposures involve long terms, such as 30 years for a typical mortgage. Community planning and of course lifetimes involve even longer time horizons. Crucially, over these longer time frames, each year is an independent annual chance, and the chance is taken again and again. So, for a long-term exposure to flooding, we really need to figure out the cumulative probability. Let's look at the 30-year cumulative probability for the previous flood hazard curve. We'll start with a 50-year return period flood, equal to an AEP of 2%, which you can see has a flood magnitude of 42 feet for this particular property. For a 30-year time frame, the cumulative probability of this flood level of 42 feet works out to be just over 45%. This tells us that over the course of a mortgage, as we take 30 repeats of that 2% chance, our overall odds of experiencing that 42-foot flood level increase to close to a coin toss. As we saw before, the 1% chance or 100-year return period flood is 48 feet. Its 30-year cumulative probability is 26%, higher than drawing a heart from a deck of cards. The 0.4% annual chance or 250-year flood of 54 feet has a 30-year cumulative probability of over 11%, higher than a 1 in 9 chance. That 0.2% annual chance or 500-year flood of 57 feet that we started with has a 30-year cumulative probability of almost 6%, about a 1 in 17 chance. Finally, let's look at a 0.1% annual chance or 1,000-year flood of 58 feet. 1,000 years sounds pretty rare. It's basically the odds of rolling snake eyes with a pair of dice twice in a row. But taken in 30-year clumps, the cumulative probability is 3%, which is about the odds of rolling snake eyes once. Keep in mind the curve uncertainty. For all of these flood levels, the 30-year probability might easily double, and the odds of having that so-called 1,000-year flood sometime over a 30-year mortgage might be more like that of rolling an 11. Now let's consider the 80-year lifetime cumulative probability for that so-called 1,000-year flood. The chance of experiencing a 30-year snake eyes flood of 58 feet rises now to 8%, or 1 in 12. Moreover, the lifetime odds for that flood level are likely to be even higher given uncertainty, maybe as high as rolling a 7. This means a decent number of folks will indeed experience a so-called 1,000-year flood in their lifetime. In fact, over a lifetime you are more likely to experience a 1,000-year flood than a major house fire. The combination of long-term cumulative probability and uncertainty shows we need to take very seriously the chance of what might seem like a very remote extreme flood. Besides repeated annual chances, there are other cumulative probabilities that might need to be considered. A property might be exposed to more than one type of flooding, more than one river, or more than one route for coastal surge. And owners of multiple properties or public agencies overseeing large regions can have multiple independent exposures. For a planning agency overseeing 5 independent exposures, the cumulative probability of a 1,000-year flood occurring somewhere in the region over a 50-year planning horizon is higher than 1 in 5. And again, estimated probabilities for extreme floods can easily be off by a factor of 2. One last point about flood hazard. Often flood professionals, public officials, and the media use the word hazard in a general way, as in threat. This is often true when they are talking about a particular flood scenario, such as a pending flood, a past historic flood, a hypothetical variation of a past flood, or a possible worst-case flood. Because they can be very useful in communicating potential flood exposure, hydrologists often develop detailed simulations of scenarios. It's easy to see that scenarios could be taken as a surrogate for hazard. But strictly speaking, flood hazard is defined using a full spectrum curve, not a particular scenario or set of scenarios. So, to summarize, 21st century wisdom says that the flood hazard for our individual property cannot be found using a simple area on a map, nor is flood hazard a score, rating, or factor. Flood hazard for each individual property is really its own mathematical curve, just like a graph of your own individual heart rate over the course of a treadmill exercise. And that curve covers the full spectrum of flood frequencies. To be sure, a flood hazard curve has significant uncertainty, so much so that it might be regarded as a scientific guesstimate. Finally, our individual flood hazard curve must consider the cumulative probability of our long-term individual exposure. In the next video, we'll examine 21st century wisdom regarding flood risk. Please don't hesitate to email, text, or call me with comments and questions.